Hi everybody. We're going to continue with the topic of graph theory and look at some particular examples that are always of interest to people who work in graph theory. We're going to talk about things that are called Euler paths and Euler circuits. This is named after a Swiss mathematician. I don't know exactly how the Swiss pronounce it, but we Americans who are not multilingual pronounce it Euler. Do the Swiss pronounce it like that? I have no idea, but I suspect they don't. But here in the United States, this is how we pronounce it. And let's look at our first definition, and then we'll look at some examples. An Euler path is a path that passes through each edge of a graph exactly once. Now remember what a path is? It's a set of ordered vertices, so there's a first vertex and a second vertex and a third and a fourth. And each vertex after the first is adjacent to the vertex that came before it. So each vertex after the first is connected to the first. Each vertex after the first is connected to the vertex that came before it by an edge. Let's look at an example of an Euler path, a path that passes through each edge of a graph exactly once. Here's a nice graph. Looks quite a bit like one of the graphs that we worked with in the first lecture. And we want to find an Euler path. So in other words, we have to find a path that includes every single edge of this graph exactly once. And for no other reason other than A is the first letter of the alphabet, let's start at vertex A. I'm going to start here and go to B. So this edge is part of the graph. The edge from A to B is part of the graph. That's our first edge. And now, call it a hunch, but I think I'm going to go this direction and go to E. We just covered this edge, D to E. And I'm going to come back home to A. Here's the edge EA or AE. And then I think I'm going to come down here to vertex C. And that covers this edge from A to C. And from here, I think it's obvious what I have to do now. I have to cover this edge from C to D. So there's edge CD. And now I go from D to B. And I've got this edge covered. And I've covered every single edge of this graph exactly once. Now you might say, oh, you started at A, and then you came back to A, so you hit vertex A twice. And you went to B, you came out of B, and then you ended up back at B. You entered vertex A twice and you entered vertex B twice. That's okay. All this says is that the path passes through each edge exactly once. Now let's see, I left vertex A, I came back to vertex A, and then I left vertex A. I was at vertex A more than once. No problem. It doesn't say anything here about how many times we can enter or leave a vertex. It just says that we can only pass through an edge exactly once. So we can go through a vertex more than once. We just can't go through an edge more than once if we have an Euler path. And in our book, they may actually just refer to this path by giving us the order of the vertices. We start at A, we go to B, we go to E, we go back to A, we go to C, we go to D, we go to B. Let's see, we started at A, then we went to B, then we went to E, then we went back to A, then we went to C, then we went to D, and then we went to B, and that was our Euler path. Our book may identify the path just by giving the order of vertices of the path and order of appearance. These are the edges of the Euler path. These are the vertices in order of appearance. Our book may represent the Euler path by listing the edges in order of appearance, or it may identify the Euler path just by listing the sequence of vertices that we start at, pass through, and end up at. Well, that was pretty easy. Let's do another one. Here's another nice graph. Kind of looks like the first one. Not exactly the same. Again, I want to create an Euler path. So my path has to pass through each edge of the graph exactly once. Let's see if I can do it. For no other reason other than A comes before these other letters, I'll start at A, and I'll go from A to B. There's my first edge. I got this edge covered. It worked well before. I'll try it again. I'll cover this edge right here, going from B to E. So there's my second edge. And I'll follow in my footsteps from the first graph. I'll go from E to A. So I've got this edge, and this edge covered exactly once. And there's only one place that I can go from here now without passing over an edge that I've already passed over. I have to go to C, which is fine because now I'm covering this edge. I just covered edge AC. And everything's going to fall into place, I think. I'll cover this edge next, going from C to E. So I've got the edge from C to E covered. And there's only one place I can go from here that I haven't already been over. There's only one path I can travel along from here that I haven't already covered, and that's the, let me start over again. There's only one vertex I can go through from here that I haven't already covered, and that's ED. So now we got this edge covered. And then I cover this last edge from D to B, and every single edge is covered exactly once. Now, in the back of the book, they may have given the vertices in order of appearance. They may define the path that way, in which case the vertices are A, B, E, A, C, E, D, and B. Let's see if that's right. We started at vertex A and went to B, and then we went to E, and then we went back to A, and then we went to C, and then we went to E, and then we went to D, and then we wound up at B. Perfect. Well, seems easy enough. Anyone can do that. What's so hard about that? Well, let's do another example. Same vertices, slightly different graph. We have 8 edges here now. We're still going to draw an Euler path, which means that we'll cover every path of this graph exactly once. We'll pass through each edge exactly once. Okay, A, B, C, D, E. Okay, I don't get an A for imagination, I'm sorry. And since I don't get an A for imagination, I guess I'll start at A again. Just because that's what I did all the times before. And I'll go from A to B, so there's this edge covered. And then I'll cover this edge again. And I got BE covered. And what the heck, I'll go back here. I got this edge, EA, covered. And from here, there's only one edge I can travel on. I have to go from A to C. That's good. So I'll go from A to C. Now I got that edge covered. And here I have a choice. I can either go to E or I can go to D. I'll go to D, what the heck. I go to D, and I got this edge covered, C to D. And if I go from D to B, I'll have to stop here because if I go from D to B, I can't leave B without traveling on an edge that I've already traveled on, but I haven't covered these 2 edges yet. So I won't do that. Instead, I'll go from D to E. So I got this edge covered. And there's only one way I can go now. There's only one edge connected to E that I haven't traveled on, so I have to go on this edge from E to C. And I'm stuck. I can't leave vertex C without traveling on an edge that I've already traveled on, and yet I haven't covered this edge yet. You know what? I think everything was going fine until I got down here. You know? I think once I got here, instead of going to C, maybe I should have gone to E instead. So I'll go from A to C, and I'll do things differently from there on. Instead of going from C to D, I'm going to go from C to E, and I'll cover this edge, CE. And now there's only one way I can go. I have to travel this edge. The only way I can leave vertex E and travel on an edge that hasn't already been passed through is if I go from E to D. So I go from E to D. And now here I have a choice. Dagnabbit. I can either go on edge DB or I can go on edge DC. But if I go on edge DB like this, then I'm stuck at this vertex, because once I get here traveling along this edge, I can't leave vertex B without traveling on an edge that I've already passed through. So I can't go this way, which means that I have to go on this edge instead. But now when I get on this edge, I'm stuck at vertex C. I can't leave vertex C without traveling across an edge that I've already passed through. So I can't leave vertex C, and yet I haven't passed through this edge yet. Well, this isn't as easy as it looks like. The first two examples were great. Maybe I shouldn't have started at vertex A. Maybe I should have started at vertex E instead. Let me try that. Let me start at vertex C, vertex E right in the middle, and see if I can do better, okay? I'm going to start at the vertex in the middle this time, and I think things will work out better. And I'm not going to go to A right away. Now I'm going to switch things up a little bit, and I'll go to vertex B. So I've just covered this edge, the edge from E to B. And now I'm going to cover this edge. I'll go from B to A. So I got that edge covered. And now what the heck, I'll go back to E. So I'll go from A to E. And what the heck, keep on going. I'll go from E to D. And if I go from D to B, I'm going to wind up at a vertex that will have, if I go from D to B, I'll be stuck at this vertex because there won't be a path for me to leave on. There won't be a path for me to leave vertex B on that hasn't already been passed through. So no, I'm not going to go from D to B right away. So I guess I'll have to go from D to C instead. Okay, D to C. And I can't go to vertex E because if I do, there won't be, if I go to vertex E, there won't be any edges leaving vertex E that haven't already been traveled across. So I can't go to E. Whoops, I can't go to A either. If I go to A, I can't leave vertex A because there are no edges leaving A that haven't already been passed through. Dagnabbit! I don't like this game anymore. I don't want to play. Well, it was fun when I was winning. Now that I'm not winning, it's not that much fun anymore. But it turns out that there's a reason, a mathematical reason why I couldn't draw an Euler path on this graph. It turns out that it's impossible. So no matter what my choice of edges was, first edge, second edge, third, no matter what my choice of edges or my sequence of vertices, it wasn't going to happen this time. I wasn't going to be able to draw an Euler path. In about 15 minutes, maybe a little bit less, we'll actually look at a theorem that tells us under which circumstances we can find an Euler path and under which circumstances we can't find an Euler path. Before we do that, I want to introduce a closely related topic, and that is Euler circuits. Euler circuits. An Euler circuit is a circuit, starts and ends at the same vertex, that passes through each edge of a graph exactly once. So an Euler circuit is a circuit that passes through each edge of a graph exactly once. Or we can look at it this way. An Euler circuit is an Euler path. Each edge is traveled across once, exactly once. An Euler circuit is an Euler path that begins and ends at the same vertex. You choose which definition you like. They're both equivalent. Now let's look at an example. Here's a nice example to start off with. And we have our old friends A, B, C, D, and E. Boy, I bet I'd be a psychologist's nightmare. But anyway, we're going to draw an Euler circuit, or we're going to try anyway. We're going to pass through every vertex exactly once, and we're going to end up right where we started. And since I have absolutely no imagination, I'm going to start at vertex A and go to B. There. We got that covered. So we just covered the edge from A to B. And what the heck? Let's go from vertex B to vertex E. We got this edge covered, B to E. And my inclination is to go from vertex E back to vertex A But if I do that, I won't be able to leave vertex A. See, if I do this, I won't be able to leave vertex A without traveling across an edge that I've already passed through. And I still have all of these edges uncovered, so I can't go to A, which means I have to go to C. So that covers vertex EC. And from vertex C, there's only one place to go, and that's vertex D. So I've got the edge from vertex C to D covered. And from here, there's only one way to go. I can go back to E. And I've covered this edge from vertex D to vertex E. And there's only one place I can go here, and that's back to vertex A. I've covered this edge, and I wind up back where I started at vertex A. I have all of the edges covered exactly once. I passed through every edge exactly once. So that's an Euler path. And I wound up back at the same vertex that I started at. So that makes it an Euler circuit too. Success. Okay, maybe I will play this game a little bit more. If we do the exercises in the book, they may give us the sequence of edges like this, or they may just give us the vertices. We start at A and go to B, and go to E, and go to C, and go to D, and go back to E, and then we go to A. This is the sequence of vertices. And in an Euler circuit, the first vertex is always going to be the last vertex. We're always going to end up at the same vertex that we started at. Now let's do another one. Here's another example. Construct an Euler circuit. This is a little bit different than what we had before. We have 6 vertices, A, B, C, D, E, F. And when we only had 5 vertices, A, B, C, D, E, I couldn't even draw an Euler path, never mind an Euler circuit. And if I can't draw an Euler path, I can't draw an Euler circuit either, because an Euler circuit is a special kind of an Euler path. So if I can't draw an Euler path, I definitely can't draw an Euler circuit. Here I want to construct an Euler circuit, and this is not exactly the same kind of diagram that I had before. It's not exactly the same kind of graph that I had a couple of examples before where I couldn't even draw an Euler path. This one, for some reason or other, I think I might be able to draw an Euler circuit. That is, an Euler path that starts and ends at the same vertex. So let me give it a shot and see what happens. I'll go from A to B, and I got this edge covered. Boy, you know, it would be great if I could have Vanna White here, and she could just write down the edges as I have them covered. Or better still, I draw an edge and she just presses the board, and the edge appears right here. Well, let's see. Maybe in next year's budget I can put in a request to have a TV supermodel And I just write down the edges, and she'll press her finger on the board, and the edge will appear here. But for now, I guess I just have to write them down myself. Anyway, I've got this edge covered. There's only one place I can go. So I'll go to vertex C. That looks good. Okay. And what the heck? From vertex C, I'll come down here to F. Got that edge covered. CF. And there's only one place I can go here. I'll go back up to A. So I've got this edge covered, F to A. And there's only one way I can go. There's only one way I can leave vertex A and travel across an edge that hasn't already been passed through. I have to go across this edge, which I will do. And I've got edge AC covered. And from here, there's only one place I can go. There's only one place that I can go. There's only one place such that I can leave vertex C and travel on an edge that hasn't been passed through. I have to go on the edge C to E. And now there's only one place that I can go. I can go from edge E to, from vertex E to vertex D. And then from vertex D, there's only one place I can go. I got to go back to A, which is nice because I have all the edges covered exactly once. And I wound up right back at the same vertex that I started at. So here's my sequence of edges. And as far as vertices go, it's A, B, C, F, A, C, E, D, A. When we do homework, the homework solutions may give just the sequence of vertices. And let's see, how am I doing this anyway? Okay, well, that was fun. Let's just do a brief retrospective. Whoops, and let me put some labels on these vertices. With this graph, I tried to create an Euler path, and I couldn't do it. And if I can't create an Euler path, I definitely can't create an Euler circuit, because an Euler circuit is an Euler path that just happens to start and end at the same vertex. I couldn't even create an Euler path for this graph. And it turns out there was a mathematical reason why I couldn't. Here, I created an Euler circuit for this graph. This is the graph we just got done working with. And so if I can create an Euler circuit, I can also create an Euler path, because every Euler circuit is an Euler path. Uh, this one doesn't look any less complicated or any more complicated than this one. Why could I get an Euler path and an Euler circuit with this graph, and I couldn't get either an Euler path or an Euler circuit with this one? It has to do with the number of edges coming into and leaving a vertex. Remember in the last lecture we defined the degree of a vertex essentially is the number of edges coming into or going out of a vertex. And then we had that special exception that a loop essentially adds 2 to the degree of a vertex. Now we don't have any loops here. We don't have any loops here. But let's just look at each vertex and look at the degree. The degree of D is 2. At E, the degree of E is 2. Here, let's say 1, 2, 3, 4. Degree of A is 4. Here, degree of E is 2. Here, the degree of C is 4. And here, the degree of B is 2. Now, we listed the degrees of every vertex, and maybe there's something special going on there. Maybe it isn't. Maybe we don't see. Let's look over here. The degree of vertex A, 1, 2, 3. The degree of C, 1, 2, 3. The degree of vertex D, 3. 1, 2, 3. The degree of vertex B, 3. And this one, E, 1, 2, 3, 4 edges coming in and going out. So degree of vertex E is 4. With this graph, we could draw an Euler circuit, we could draw an Euler path. And it has something to do with the degree of the vertices. With this graph, we couldn't draw an Euler path, we couldn't draw an Euler circuit, we couldn't do anything. And it has something to do with the degree of the vertices. Do you see it? This graph, let's see, look at the degrees. 2, 4, 2, 2, 4, 2. The degree of each vertex is even. There are no vertices of odd degree. Here, degree 3, degree 3, degree 4, degree 3, degree 3. We have 4 vertices of degree 3, which means that we have 4 vertices whose degree is odd. That's going to be a very crucial factor. Doesn't seem like it should be, but in fact, that's what's behind whether or not we can draw Euler paths and Euler circuits on a graph. And I'll put the results up right now. I apologize. Apparently, I had the recorder off when I was doing the lecture. And then when I paused for the lecture, I found out, here's what I'm going to have to do. I'll just do this whole spiel over again. Here's the theorem that tells us when we can construct Euler circuits and when we can construct Euler paths, and when we can't construct Euler circuits and when we can't construct Euler paths. First of all, the graph has to be connected. By definition, an Euler path or an Euler circuit exists only on a connected graph. So if the graph's not connected, don't even think about Euler circuits, Euler paths, there ain't going to be any. So suppose we have a connected graph. In other words, there's a path going from any vertex to any other vertex. If a graph has no vertices of odd degree, in other words, all of the vertices are of even degree, then an Euler circuit can be constructed starting at any vertex and ending at that same vertex. Well, if we can construct an Euler if we can construct an Euler circuit at any vertex and have it end at that vertex, we can surely construct an Euler path starting at any vertex, because every Euler circuit is also an Euler path. An Euler circuit is an Euler path that just ends up at the same vertex that it starts at. And if we have no vertices of odd degree, then an Euler circuit can be constructed starting at any vertex and ending at that vertex. And that means that we can also start an Euler path starting at any vertex. Next, if a graph has exactly two vertices of odd degree, at least one Euler path can be constructed, but no Euler circuits can be constructed. And each Euler path must begin at a vertex of odd degree and end at the other vertex of odd degree. So if we have two vertices, exactly two vertices of odd degree, no Euler circuits. We can, however, construct an Euler path, but we have to be careful. We have to start at one vertex of odd degree and end at the other vertex of odd degree. And if a graph has more than two vertices of odd degree, it ain't got none. Neither an Euler path nor an Euler circuit. Wait a minute now. No vertices of odd degree, exactly two vertices of odd degree, more than two vertices of odd degree. They didn't say anything here about what happens if we have exactly one vertex of odd degree. And here's why. It's impossible. It is impossible to have a graph that has exactly one vertex having odd degree. So they actually didn't leave out any cases here. And notice something. If a graph has no vertices of odd degree, then we can construct an Euler circuit and an Euler path. If a graph has exactly two vertices, no Euler circuits. If a graph has more than two vertices of odd degree, no Euler circuits. So in order to have an Euler circuit, the graph can't have any vertices of odd degree. The vertices all have to be of even degree. And remember the two examples that we looked at before I put this mess on the board? We had one graph where I was able to draw an Euler circuit, and another graph where I couldn't. And then we wrote down the degree of each vertex. Well, do you remember the graph that had an Euler circuit? All of the vertices were of even degree. And that has to be the case. In order to have an Euler circuit, all of the vertices of the graph have to be of even degree. If we have two vertices of odd degree, we're not going to get any Euler circuits, but we can construct Euler paths provided that the path starts at one vertex of an odd degree and ends at the other vertex of odd degree. And if the graph has more than two vertices of odd degree, we don't have Euler anything. We don't have Euler paths, and we don't have Euler circuits. Now, before I erase all of this, I'm going to look at an example that addresses what's said here in point 2. We're going to look at a graph that has exactly two vertices of odd degree, and we're going to draw Euler paths. Remember what we were just saying? If a graph has exactly two vertices of odd degree, we can construct at least one Euler path, but no Euler circuits. And they tell us how to go about constructing the Euler paths. They say, each Euler path must begin at a vertex of odd degree and end at the other vertex of odd degree. So let's look at this example. Vertex A has degree 2. Vertex D has degree 2. Vertex B has degree 3. Vertex C has degree 3. So we have two vertices of odd degree, B and C. And we should be able to draw a path from one to the other. So I'll start at B and go to A. Here's my edges. And then I'm going to go, the only place I can go is from A to C. So I got this edge covered, this edge covered. And let's see, where do I want to go? Maybe I'll go this way. So I just covered that edge. I go from C to B. And then I'll go from B to D. And from D, I'll go to C. And I've covered every path exactly once. And if we're characterizing the graph by the sequence of vertices, then we're going to go B to A to C to B to D to C. B, A, C, B, D, C. We started at vertex B. We went to A. We went to C. We went to B. We went to D. We went to C. We started at one vertex of odd degree, and we ended at the other vertex of odd degree. Now, could we have started at C, the other vertex of odd degree, and gone to B? Absolutely. And we would have gotten a path, a different path, because we're starting at a different vertex. What the heck? Do I need to do this? Maybe I do. Okay, we'll start our path at the other vertex of odd degree. And what the heck? I'll go from C to A. So I got this edge covered. There's only one way I can go from here. I'll go from A to B. So I've got this edge covered. Then I'll go from B to C. I got this edge covered. And now there's only one way that I can leave C and travel on an edge that hasn't been passed through. I'll go from C to D. And then there's only one way I can go. I'll go from D to B. And I've covered every edge. So we started at C and went to A, then we went to B, then we went back to C, then we went to D, then we went to D. We started at C, we ended up at B. We started at one vertex of odd degree, we ended up at the other vertex of odd degree. But before we do another example, I just want to refresh our memories about a term, a bridge. A bridge is an edge of a connected graph. So if the graph's not connected, then there's no such thing as a bridge. A bridge is an edge of a connected graph, which if removed, results in the graph being disconnected. Is there any edge here in this graph that if we remove that edge would make the graph disconnected? You're probably thinking the edge that goes from vertex C to vertex D. If we remove that edge, the graph is indeed disconnected. So edge CD is a bridge. Now we'll get on to our example. Here's an example. Use Flurry's algorithm to determine an Euler path. Well, there's not really much to this algorithm that's not completely common sense except for one thing. And that is, don't cross a bridge unless you absolutely have to. Crossing a bridge should be a last resort. They tell us to find an Euler path, and we have two vertices of odd degree. So if we find an Euler path, it has to start at one of these vertices, and it has to end at the other. So let's say that we start here, okay? We're going to start at this vertex of odd degree. We can go from C to A, or we can go from C to B, or we can go from C to D. If we go from C to D, we're crossing a bridge and we don't absolutely have to do that. So we are not going to go from C to D right away. So instead, let's go from C to A. And then let's go from A to B. It's the only way we can go. Boy, it sure would be nice to have Vanna White over here and just have her press her finger on the board and the edges just pop up. Vanna, where are you when we need you? Okay, what next? We go from B back to C. It's the only way we can go. And now we have to cross the bridge. But that's okay because we've covered every edge up here. Once we cross the bridge from C to D, we don't ever have to come back here because we've got all the edges covered. So then we go from C to D. And we can either go from D to E or D to F, and it won't matter which one we choose. So we'll go from D to E. And we'll go from E to F. And then finally, we'll go from F to D. And we got ourselves a path. Now, if we specify just the vertices, we go from C to A to B to C to D to E to F. C, A, B, C, D, E, F, D. And again, essentially, it's the first letter of each vertex. Except for the last one. The last edge, we give both the first and the last vertex. The answer in the back may just give the sequence of vertices. And notice something. Sooner or later, if we have a path, we're going to have to cross this bridge because every edge has to be crossed or covered. But we didn't cross this bridge until we had covered all of the edges up here. And then it was okay to cross. Okay, let's take this graph. Use Flurry's algorithm to determine an Euler path. And we weren't just born yesterday, were we? We look at this and we go, what? Wait a minute now. Here's one vertex of odd degree. Here's another vertex of odd degree. Here's another vertex of odd degree. Here's another vertex of odd degree. With or without this algorithm, we're not going to be able to construct an Euler path because we have more than two vertices of odd degree. We can't construct an Euler path. If we have more than two vertices of odd degree, there ain't no Euler nothings. No Euler paths, no Euler circuits, no Euler nothings. So before we even start, we look at the graph and say, is it even possible to draw a path? Are there more than two vertices of odd degree? Yup, 1, 2, 3, 4. Okay, can't be done. Let's move on to the next exercise. use Flurry's algorithm to determine an Euler circuit. And you know, last time I checked, there should have been an E at the end of the word determine. Okay? We're going to construct an Euler circuit, I hope. Now again, let's not try to do something that's not possible. Before we start, is it possible? Take each vertex. A, what's the degree? 2. B, what's the degree? 2. C, what's the degree? 2. D, what's the degree? 1, 2, 3, 4. E, what's the degree? 1, 2, 3, 4. F, what's the degree? 2. All of the vertices are of even degree, so it is possible to construct an Euler circuit. As a matter of fact, we can start at any vertex that we want. What the heck? Let's just start at F. We'll start right here, and let's go to B. Okay, we go from F to B. And from B, there's only one way we can go, B to E. What do you say? Let's go to A. E to A. And from A, I don't know, what do you, oh, we can only go one way. From A, we have to go to D. And from D, we can either go to E to C and back to D, or we can go from D to C to E and back to D. Let's go from D to C. From C, there's only one place we can go. We got to go to E. From E, there's only one place we can go. We've got to go to D. And from D, there's only one place we can go, and that's back to F. Holy moly, we completed the circuit. We started at F, we ended up back at F. And if we're just listing the vertices in order of appearance, we started at F, we went to B, we went to E, we went to A, we went to D, we went to C, we went to E, we went to D, and we went to F. We ended up at F. Let's see, did I miss any? Started at F, then we went to B, then we went to E, then we went to A, then we went to D, then we went to C, then we went to E, then we went to D, and we wound up at F. Okay. Before I cut you loose, there's one other thing that I should show you, just because we're going to have an exercise or two that uses this type of modeling for graph theory. I'm going to mention this because we'll have to do some examples that require us to model the floor plan of a building using graph theory. So here's a typical building. Wherever we have an opening like this, that represents a doorway. This is a doorway, that's a doorway, that's a doorway, that's a doorway, that's a doorway. This is a doorway, this is a doorway, this is a doorway, this is a doorway. Each room is represented by a vertex. So in our graph, we'll represent room A by vertex A, we'll represent room B by vertex B, and so forth. And the hallway I'm going to be real original. I'm going to have the hallway represented by vertex H. And notice this bullet point, the outside of the building is represented by the vertex O. Maybe I should mention, emphasize that. Outside represented by the vertex O for outside. And in our graph, two vertices are adjacent exactly when the rooms that they represent share a doorway. For example, room B and room C share a doorway, so the vertices representing room B and room C will be joined by an edge. They'll be adjacent. Okay, let's see how we do this. You know what? I'm tempted just to have vertices A, B, C stand side by side like this. And in the middle we have the hallway, vertex H. And then down here, room D, E, and F, vertex D, vertex E, vertex F. And maybe I should move my labels up here like this. Now, am I missing anything? Oh, my vertex O, I don't have that. And let's see, I guess I'll just put vertex O out here. Notice that every room, A, D, B, E, C, F, is connected to the hallway, as is the outside of the building. Here's the outside. And it's connected to the hallway by two doors, actually. Now that's interesting. So there's one edge going to the hallway, and here's another edge going to the hallway from vertex O. Every other room is connected to the hallway. Are we done? No. Some of these other rooms are connected to each other by means other than the hallway. There's a door that's shared by room A and room B. There's a door that's shared by room B and room C. And, room D and room E don't share a door. Room E and room F don't share a door. So that looks like it then. This is our graph that represents the rooms of the building and the outside. Now let's see if this works. A is connected to room B, or rather room A and room B share a door. Yes, they do. Room A and the hallway share a door. Yes, they do. Room B and room A share a door. Yes. Room B and the hallway share a door. They sure do. Room C and room B share a door. Yes. Room C and the hallway share a door. Yes. Okay. The outside shares one doorway with the hallway. The outside also shares another doorway with the hallway, so that works. D shares a door with the hallway, and that's it. That's true. E shares a door with the hallway. That's true. F shares a door with the hallway, and that's it. Okay, so that's our graph that illustrates the floor plan of a building.